in Unit 3, Block 1. This is the first page. So in this example, it says Acme gets a consumer demand of 1,300,000 widgets when they're giving them away for free. But the number of widgets sold decreases at a continuously compounding rate of 3% for every dollar that they increase the price. So notice here, if you think about this graphically, we're inputting P, price, outputting demand, number sold, D of P, and they're telling us that we have a point, input a price of 0, output 1,300,000 sold, and that it's decreasing at a continuously compounding rate of 3%, which means it's an exponential function, a decreasing exponential function. So we know that our exponential function has y-intercept 1,300,000. It's decreasing at a continuously compounding rate of 3%, so it's e to the negative 0.03 p. There's our demand function. It asks us now to write a formula for revenue. We know revenue is number sold times price per item. So our R of P function, number sold, which is D of P, so 1,300,000 e to the negative 0.03 p, times price per item, which is P. Now traditionally I would put this P, I'd squeeze it here in between the 1,300,000 and the exponential. It doesn't matter, it's up to you, but generally I think it would be more conventional to write 1,300,000 P times e to the negative 0.03 p. Again, it doesn't matter, it's just probably more common to see it this way. All right, so we have a revenue function, and it says here R prime of 33.33 is 47.83, and it goes a little tiny bit to the right. R prime of 33.34 is negative 95.63. It says write a complete sentence to interpret the real-world meaning of both. So remember, we're inputting in this function P, and that's price, 33.33, and it's outputting revenue. So they're saying when charging $33.33 per item, revenue is increasing at a rate of $47.83 revenue per $1 increase in price. They're saying if you increase the price by a penny, so now they're charging a price of $33.34 per item, then the derivative is negative. So revenue is decreasing at a rate of $95.63 of revenue per $1 increase of price. So notice those prices are only 1 penny apart. So in part D and part E here, it's kind of putting those two ideas together. It's saying describe what you know about R of P based on the fact that this one's positive and this one's negative, and sketch it. Kind of think about what does R of P actually look like. So I'm going to start drawing the sketch down here. Our revenue function, if you go to P equals 33.33, revenue is increasing. So R is increasing because the derivative's positive. But then if you go over just a tiny bit to the right to P equals 33.34, now the derivative is negative, so R is decreasing. Just a penny apart, and it changed from R increasing to R decreasing. So it kind of makes you think that it must have, at a point in between, reached a peak, reached a maximum. So the fact that R prime was positive means R was increasing at that instant. And when R prime was negative, we know R is decreasing at that time. So if you think about the graph of revenue, it's going up, and then just slightly to the right it's going down. So it makes us think there's going to be a maximum at the point in between. So somewhere around there exists the price at which revenue is highest, the price they should charge to get the highest revenue. So our goal here, huge goal in Unit 3, is to be able to identify maximums and minimums. So our first definition is just a reminder of what a critical point is. So we've seen these before. Remember, a continuous function f has a critical point at x equals a if f prime is undefined at x equals a, or if f prime is 0 at x equals a. So when the derivative is 0 or when the derivative is undefined and it's actually a point on your function f, then we call that point a critical point. So notice what that would mean about your function f. If f prime is 0, that means f is flat right at that instant. And if f prime is undefined, we're going to draw that in a minute, but it could be the case that you have a sharp point on f, or it could be the case that f is vertical for just an instant. We don't see that too much in this class, but we will look at a couple examples like that. So our first theorem here is if x equals a is a local extrema point, extrema, the very, very highest, the very, very lowest, so a local max or a local min. So if x equals a is a local max or a local min for your function f, then you are guaranteed that x equals a is a critical point. So let's draw some examples of that. So for example, if in a little local region the graph of f of x looks like this, it's got a little hump in the graph, and here at the tippy top is x equals a. You see the way I've drawn this, that we have a local max, the very highest point in the local region at x equals a. Now, the theorem says if you have a local max or min on f of x, then you're guaranteed that that point is a critical point. Notice on the graph I just drew, at this point in the tippy top, on that local max point, the derivative at that instant, f prime of a, would equal 0. On the left side, the derivative is positive because the function f is increasing. On the right side, f prime is negative because f of x is decreasing. Right in between, it changed from positive to negative, it became 0. Notice at the tippy top, if you drew the tangent line, it would be flat. Similarly, if you had a little hump graph that's upside down like this, with x equals a at the very bottom, so in that little local region, that is a local minimum. It's the lowest point in that local region. Again, notice at this local minimum, if you drew the tangent line at that instant, it would be a tangent line that is horizontal, flat. At that instant, when you have a local minimum, f prime of a is 0. So at a local max, at a local min, we see that point is a critical point. There is a couple other instances. Let's draw the example of f of x equals absolute value of x. The absolute value function is actually two functions put together. On the left side of the origin, it's the function y equals negative x. It's got slope -1. Then it abruptly changes once you hit the origin and starts to become y equals positive x with slope +1. So if we think about the derivative of this, over here on the left side of the origin, f prime is -1. And over here on the right side of the origin, f prime is +1. So of course the question becomes, what is f prime right at the instant when x is 0, right when it changes from being y equals x to y equals negative x, or y equals negative x to becoming y equals x? And the answer is that f prime of x does not exist. It is undefined. It does not exist at x equals 0. F prime is undefined. The limit of the slopes from the left is not equal to the limit of the slopes from the right. The limit of the average rates of change on the left side are -1, and the limit of the average rates of change on the right side are +1. The left-hand limit doesn't equal the right-hand limit, so the limit overall does not exist. Okay? For this reason, there actually is no derivative at that instant. The function f exists, but it doesn't have a derivative at that instant. So this is a critical point. Remember what we said about critical points. We said critical points are places where the derivative is 0 or places where the derivative is undefined. So here is a place where the derivative is undefined. Back to our theorem again. It said, if x equals a is a local extrema point, so if it's a local max or local min, then you are guaranteed that it's a critical point. So look at our graph here, our little absolute value function. This is a local minimum. It's the lowest point in that local region, and look, it's a critical point. It's a place where the derivative is undefined. It'd be the same thing if it were an upside down sharp point type graph. We have a positive slope, and then abruptly it changes to become a negative slope. At this instant, I see on the graph I've drawn we have a local max, and it's a critical point. It's a place where the derivative is undefined. All right, so this theorem is just reminding us if you have a local max or a local min, you are guaranteed that it is a critical point. The reverse is not true. All right, this is extremely important, and really the entire reason that we're going to be spending the next few days working on the first derivative test. If you have a critical point, it is not necessarily an extrema point. Critical points are not necessarily maxes and mins. So when we find critical points, you're going to have to test to see if they are maxes and mins. Let's first of all just draw some examples where we have critical points that are not max and min. So let's start with something like so. Let's say we have an increasing concave down function, and it's getting flatter, flatter, flatter until it actually reaches x equals a, where f prime of a is 0. It actually flattens out. F of x is flat for an instant. Now, if this graph after x equals a proceeded downward, then that would be a maximum. But it's possible that your graph just keeps increasing like so. So it's flat for an instant. F is flat for an instant. So x equals a is a critical point. But notice it's definitely not the highest point in its local region, and it's definitely not the lowest point in its local region. So x equals a is not a local extrema. It's not a max, and it's not a min, but it is a critical point. So it's possible to have places where the derivative is 0 that are not max or min. Similarly, maybe your graph is going down and it's concave up and it flattens for an instant. F prime of a is 0. And instead of then turning and going back up, where it would be a minimum, maybe it just keeps going down like this. So now x equals a is a critical point. It's a place where the derivative is 0. But x equals a is not a max, and it's not a min. It's not the very highest, not the very lowest in its local region. All right, another variety of this is when we could have a function getting steeper, steeper, steeper until it actually reaches a point at x equals a where f is vertical for an instant, for just at that one instant in time it's vertical, and then it turns and goes like this. At this instant, f prime of x is undefined. So again, this is a critical point. But again, clearly, it's not a max, it's not a min. So it's a critical point that's not a max or min. All right, so the point of this is we want to find maxes and mins. We want to find maximum profit, minimum cost. These are important things to be able to find. We know if we have a max or min, it's definitely going to be a critical point. But we also know if you find a critical point, you're not guaranteed that it is a max or a min. So what we're going to do is put these ideas together, and we're going to create this test called the first derivative test that helps us identify local maximum and local minimum from a given function. All right, step 1, if you're going to find a maximum minimum, find critical points of the function f. Recall what that means. You need to find where is f prime of x equal to 0? Where is f prime of x undefined? Those are the places that you have critical points. Second, you're going to create a little number line covering the entire domain of f, and you're going to label your critical points on that line. So in order to explain this, let me just create a little example. Let's say up in step 1, we identified critical points, and let's say we had a critical point at x equals -2 and x equals 3 and x equals 7, right? Just as an example. Let's say those are the places where the derivative is 0 or the derivative is undefined. Those 3 critical points. In number 2, you create a number line. So for example, I would just draw a number line. Let's say the domain of my function f is all real numbers. So here's the number line with all real numbers. And in order, I'm just going to put right on that number line. Here's x is -2. Over this way is x equals 3. And over this way is x equals 7. So I put my critical values on the number line. These are places where the derivative is 0 or the derivative is undefined. These are the only places where the derivative is 0 or the derivative is undefined. Nowhere else. If there were other places where the derivative was 0 or undefined, I would have found them in step 1. This is it. What that means is that I can now say that everywhere else, every other interval, the derivative is either trapped up here above the x-axis or trapped below the x-axis. So for example, let's say the derivative function over here at x is, we'll say -5 in this little interval. Let's say f prime of -5 is 10. So it's up here. It is not possible that f prime of x is up here above the x-axis, and then you get a little closer, and maybe it's down here, and you get a little closer, and suddenly it's down below the x-axis and becomes negative. That's not possible because if that were to happen, f prime would have had to either cross the x-axis, thus creating another critical point, which can't happen because we said these are the only critical points, -2, 3, and 7. So that can't happen. It cannot be positive and then suddenly become negative. That can't happen. Alternatively, I just erase that. You could have jumped over the x-axis. So let's say at -5, the derivative is +10. So f prime of -5 is 10. And then suddenly it jumps over the x-axis, doesn't hit it, it just leaps over the x-axis, and maybe f prime of -3 is -5. Okay, so now it's negative. That can't happen either, because if it jumps over the x-axis, that means there exists a point here where f prime would be undefined. But again, that can't be the case, because we said these 3 are the only critical points. X is -2, x is 3, x is 7. F prime can't be undefined over here to have it leap over the x-axis because that would be another critical point. So what we now have is we have taken our real number line, we've identified the 3 places where the derivative is 0 or the derivative is undefined, and on the intervals that you've now created, the interval below -2, the interval between -2 and 3, the interval between 3 and 7, and the interval after 7, on these 4 intervals, the derivative is entirely trapped above the x-axis or below the x-axis. And all I now need to do is I'm going to pick any value, any x value on the interval, plug it into the derivative, and see where the derivative is. So for example, I pick x equals -5, because it's down here below -2. I plug it into the derivative. Let's say I plug in -5 into the derivative function, and I get out a positive number. That means the derivative is positive. F prime is positive. And that means f prime is positive on this entire interval below x is -2. That means f is increasing on that entire interval below x equals -2. Now I'm going to pick a value between x is -2 and x is 3. So for example, let's say I pick 0. I plug it into the derivative. Let's say I get f prime of 0 is negative. So now between x is negative 2 and x is 3, the derivative is some negative number, and that is true for all x's on this interval. Remember, it cannot change. It has to be trapped. Since the derivative is negative on this interval, we know f is decreasing on this interval. I again pick between x is 3 and x is 7, so let's say maybe I pick x is 5. I plug x is 5 into the derivative. Let's say this time I got negative. That means on this entire interval, f prime is negative. That means on this entire interval, f is decreasing. And lastly, I pick a number up here above x is 7, like x is 10. Any x value up here would work though. F prime of 10, let's say it's positive. So that means f prime is positive on this entire interval above x equals 7. And so f is increasing on this entire interval above x equals 7. What I've concluded here is I have a function f that is increasing, and then at x equals negative 2, it's flat for an instant at the critical point. And then after x equals negative 2, f is decreasing until it flattens again at x equals 3, because that's the place where the derivative is 0. And then it says between x equals 3 and 7, f is still decreasing. So it's going down, 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 like so. But at x equals 7, it's flat again. And then after x equals 7, f is increasing. What I've now done is I've really created a shape description of f of x. F of x increasing, f of x flat at x equals 2. F of x decreasing, then f of x flat at x equals 3. F of x decreasing again, then f of x flat at x equals 7, and then f of x increasing. So it looks roughly like this. I see x equals negative 2 is a local max. Why did that happen? Because on the left side of x equals negative 2, f prime was positive, and on the right side of x equals negative 2, f prime was negative. I can also conclude that x equals 3 is not a min, and it is not a max, because on the left side of x equals 3, f prime is negative, and on the right side of x equals 3, f prime is still negative. The derivative did not change sign, so f of x did not turn. But I can conclude that x equals 7 is a local min, because on the left side f prime is negative, and on the right side f prime is positive, so f is decreasing then increasing.